It is important to understand which National Electrical Code, or NEC, edition is being referenced when discussing or answering electrical code questions. The NEC is updated regularly, typically every 3 years, and different states and jurisdictions may adopt different versions of the code. This can lead to significant variations in the requirements for electrical installations. For example, a rule that is in effect in one state based on the 2020 NEC might not be applicable in another state that is still using the 2017 or 2015 NEC. Because of these differences, it's essential to know which code edition is being used to ensure accurate interpretation and application of the rules. When someone provides an answer to an electrical code question without specifying the code edition, it can create confusion and potentially lead to non-compliant or even unsafe installations. For those working in the electrical field, or anyone dealing with electrical installations, verifying the applicable code edition is critical before making any decisions or taking any action. If the code edition isn't explicitly stated, it's always best to ask for clarification to avoid any misunderstandings. Understanding the structure and organization of the NEC is also vital. The NEC is divided into chapters, articles, and sections, each covering specific aspects of electrical installations. Chapters 1 through 4 contain general requirements. Chapters 5, 6, and 7 address special occupancies, special equipment, and special conditions, and Chapter 8 covers communication systems. Within each chapter, articles provide more detailed rules for specific topics, and sections offer specific requirements for particular situations. For example, Article 250 covers grounding and bonding, and it includes various sections addressing different grounding and bonding methods and requirements. The NEC uses a numbering system to organize its content. Each section is identified by a number that indicates the chapter, article, and section. For example, Section 300.22c refers to Chapter 3, Article 300, Section 22, subsection C. Understanding this numbering system helps in locating specific requirements within the code. Code references are crucial for several reasons. Firstly, they provide a clear and unambiguous way to identify the specific rule or requirement being referenced. This eliminates any ambiguity or misinterpretation that could arise from simply describing the rule in general terms. Secondly, code references allow others to easily verify the accuracy of the information being presented. By looking up the reference code section, anyone can confirm that the information is consistent with the actual requirements of the NEC. Thirdly, code references facilitate communication and collaboration among electrical professionals. When everyone is using the same code references, it's easier to discuss and understand complex electrical issues. Grounding and bonding are essential for electrical safety. Grounding provides a low impedance path for fault current to return to the source, which helps to trip the overcurrent protective device and clear the fault. Bonding connects non-current carrying metal parts together to create an electrically conductive path, which minimizes the voltage difference between these parts and reduces the risk of electric shock. Article 250 of the NEC covers the requirements for grounding and bonding. It specifies the types of grounding and bonding conductors that are permitted, the methods for installing these conductors, and the requirements for connecting them to the grounding electrode system. Some key requirements in Article 250 include the following. The grounding electrode system must consist of one or more grounding electrodes, such as a metal underground water pipe, a ground ring, or a rod or pipe electrode. The grounding electrode conductor must be sized according to Table 250.66 of the NEC, based on the size of the service entrance conductors. The bonding conductors must be sized according to Table 250.102, based on the size of the overcurrent protective device protecting the circuit. All non-current carrying metal parts of electrical equipment must be bonded together, including enclosures, raceways, and equipment frames. Overcurrent protection is another critical aspect of electrical safety. Overcurrent protective devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. When an overcurrent occurs, the protective device interrupts the flow of current, preventing damage to the equipment and reducing the risk of fire or electric shock. Article 240 of the NEC covers the requirements for overcurrent protection. It specifies the types of overcurrent protective devices that are permitted, the methods for installing these devices, and the requirements for selecting the appropriate size and rating of the devices. Some key requirements in Article 240 include the following. Overcurrent protective devices must be readily accessible. Overcurrent protective devices must be protected from physical damage. Overcurrent protective devices must be rated for the available fault current. The rating of the overcurrent protective device must not exceed the ampacity of the conductors it protects, except as permitted by specific exceptions in the NEC. Wiring methods refer to the way electrical conductors are installed and supported. The NEC recognizes a variety of wiring methods, each with its own set of requirements and limitations. Some common wiring methods include rigid metal conduit, intermediate metal conduit, electrical metallic tubing, flexible metal conduit, non-metallic conduit, and cable assemblies. Chapter 3 of the NEC covers the requirements for wiring methods and materials. It specifies the types of conductors and raceways that are permitted, the methods for supporting and securing the wiring, and the requirements for protecting the wiring from physical damage. Some key requirements in Chapter 3 include the following. Conductors must be insulated for the voltage and temperature conditions to which they will be exposed. Raceways must be installed in a complete and mechanically sound manner. Wiring must be supported and secured at intervals specified in the NEC. Wiring must be protected from physical damage such as abrasion, impact, or exposure to corrosive substances. Special occupancies and equipment present unique electrical safety challenges. The NEC includes specific requirements for these types of installations to address the increased risks associated with them. Chapter 5 of the NEC covers special occupancies such as hazardous locations, healthcare facilities, and places of assembly. Chapter 6 covers special equipment such as electric signs, swimming pools, and elevators. Some examples of special requirements for these types of installations include the following. Hazardous locations require explosion-proof or intrinsically safe equipment to prevent ignition of flammable gases or vapors. Healthcare facilities require isolated power systems to protect patients from electric shock. Places of assembly require emergency lighting and power systems to ensure safe evacuation in the event of a power outage. Swimming pools require ground fault circuit interrupters to protect swimmers from electric shock. Electric signs require disconnect switches to allow for safe maintenance and repair. Understanding the NEC is a continuous process. The code is updated regularly, and new technologies and installation methods are constantly being developed. To stay up to date, it's important to participate in continuing education courses, attend industry events, and read trade publications. It's also helpful to consult with experienced electrical professionals and code officials to get their insights and perspectives. By staying informed and engaged, electrical professionals can ensure that they are providing safe and compliant electrical installations. When determining the correct wire size for an electrical circuit, several factors must be considered to ensure safety and prevent overheating or voltage drop. These factors include the ampacity of the wire, the ambient temperature, the number of current-carrying conductors in a raceway or cable, and the length of the circuit. The ampacity of a wire is the maximum amount of current, in amps, that the wire can safely carry without exceeding its temperature rating. The NEC provides tables that list the ampacities of different sizes and types of wires based on their insulation type and temperature rating. For example, Table 310.16 of the NEC lists the ampacities of insulated conductors rated up to 600 volts based on ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. It's important to select a wire size that has an ampacity equal to or greater than the non-continuous load plus 125% of the continuous load. A continuous load is defined as a load that is expected to operate for 3 hours or more at a time. For example, if a circuit will supply a continuous load of 20 amps, the wire must have an ampacity of at least 25 amps, which is 20 amps multiplied by 1.25. Ambient temperature is the temperature of the surrounding air or environment in which the wire is installed. If the ambient temperature is higher than 30 degrees Celsius, the ampacity of the wire must be derated or reduced to account for the increased heat. The NEC provides correction factors for different ambient temperatures in Table 310.16. For example, if the ambient temperature is 40 degrees Celsius, the ampacity of a wire with a temperature rating of 75 degrees Celsius must be multiplied by a correction factor of 0.88. The number of current-carrying conductors in a raceway or cable can also affect the ampacity of the wires. When multiple current-carrying conductors are installed in close proximity to each other, the heat generated by the conductors can raise the temperature of the wires and reduce their ampacity. The NEC provides adjustment factors for different numbers of current-carrying conductors in Table 310.15 cone. For example, if there are 4 to 6 current-carrying conductors in a raceway or a cable, the ampacity of the wires must be multiplied by an adjustment factor of 0.80. Voltage drop is the decrease in voltage that occurs along the length of a circuit due to the resistance of the wires. Excessive voltage drop can cause equipment to operate inefficiently or even fail. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To calculate voltage drop, you can use the following formula. Voltage drop equals 2 multiplied by K multiplied by I multiplied by D divided by the circular mils of the wire, where K is the direct current constant, which is approximately 12.9 ohms for copper and 21.2 ohms for aluminum. I is the current in amps. D is the one-way distance of the circuit in feet. Circular mils is the cross-sectional area of the wire. After calculating the voltage drop, compare it to the recommended limits. If the voltage drop exceeds the limits, you will need to increase the size of the wire to reduce the resistance and lower the voltage drop. Here's an example of how to determine the correct wire size for a circuit. Suppose you need to install a 20 amp circuit to supply lighting in a commercial building. The circuit will be wired with type THHN copper conductors, which have a temperature rating of 75 degrees Celsius. The ambient temperature is 30 degrees Celsius, and there will be 3 current-carrying conductors in the raceway. The one-way distance of the circuit is 100 feet. Firstly, determine the minimum ampacity of the wire. Since the load is 20 amps and will likely operate for 3 hours or more at a time, it's considered a continuous load. Therefore, the wire must have an ampacity of at least 25 amps, which is 20 amps multiplied by 1.25. Secondly, check the ampacity of different wire sizes in Table 310.16 of the NEC. A number 12 AWG THHN copper conductor has an ampacity of 30 amps at 30 degrees Celsius. A number 14 AWG THHN copper conductor has an ampacity of 20 amps at 30 degrees Celsius. Since the minimum ampacity required is 25 amps, a number 12 AWG conductor is needed. Thirdly, apply any necessary derating or adjustment factors. Since there are 3 current-carrying conductors in the raceway, apply the adjustment factor from Table 310.15 current. For 3 current-carrying conductors, the adjustment factor is 0.80. Multiply the ampacity of the number 12 AWG conductor by the adjustment factor 30 amps multiplied by 0.80 equals 24 amps. The adjusted ampacity of the number 12 AWG conductor is 24 amps, which is less than the minimum required ampacity of 25 amps. Therefore, it will be necessary to use a larger wire size or reduce the load on the circuit. If a number 10 AWG THHN copper conductor is used, it has an ampacity of 35 amps at 30 degrees Celsius. Multiplying the ampacity of the number 10 AWG conductor by the adjustment factor, 35 amps multiplied by 0.80 equals 28 amps. The adjusted ampacity of the number 10 AWG conductor is 28 amps, which is greater than the minimum required ampacity of 25 amps. Therefore, a number 10 AWG conductor can be used. Fourthly, calculate the voltage drop. Use the voltage drop formula. Voltage drop equals 2 multiplied by K multiplied by I multiplied by D divided by the circular mils of the wire, where K is 12.9 ohms for copper, I is 20 amps, D is 100 feet, and the circular mils of a number 10 AWG conductor is 10,380. Voltage drop equals 2 multiplied by 12.9 ohms multiplied by 20 amps multiplied by 100 feet divided by 10,380 circular mils. Voltage drop equals 4.97 volts. Fifthly, determine the percentage of voltage drop. To do this, divide the voltage drop by the source voltage and multiply by 100%. Assuming the source voltage is 120 volts, the percentage of voltage drop is 4.97 volts divided by 120 volts multiplied by 100% equals 4.14%. Since the percentage of voltage drop is greater than the recommended limit of 3% for branch circuits, it may be necessary to increase the size of the wire to reduce the voltage drop. In this case, using a number 8 AWG THHN copper conductor would reduce the voltage drop to below 3%. In summary, to determine the correct wire size for an electrical circuit, it is essential to consider the ampacity of the wire, the ambient temperature, the number of current carrying conductors, and the voltage drop. By following the requirements and recommendations of the NEC, you can ensure that the circuit is safe and performs as intended.